Hello again, this is the Pencrest High School AP Physics 1 video series. This is video 8B, simple harmonic motion. Now, harmonic oscillation is exhibited by mechanical systems that have wave properties like frequency, period, and amplitude. The descriptor simple, to go with simple harmonic motion, implies that there's no energy loss over time. This is an idealization. Again, it's a model. Real mechanical systems typically lose energy to friction, in which case we call them damped. We'll get to that a little bit later. Any harmonic oscillator wants to go back to its equilibrium position no matter how they are disturbed. This is called the restoring force. It tends to point back towards the equilibrium position no matter how the system is displaced. So that's the nature of a harmonic oscillator. The restoring force points back to the equilibrium position. So the first thing we'll look at is a simple pendulum. We have a string or a rope with a mass on the end of it. The mass on the end is often called a bob. If the bob is lifted and the rope is kept tight, the net force will point back towards the rest position. The pendulum will swing down through the rest position. It'll swing back up to the same height on the other side, assuming there's no loss due to friction. If you read this sequence from left to right, the bob swings down through the rest position, swings back up to the other side, and then back down through the rest position, and it goes back and forth and back and forth. The restoring force in this case is the combination of the tension in the string and the gravitational force on the bob. The net force will point towards the rest position. If you look at the bob here, we've got mg down and the ft, the tension, pulling this way. The net force then would point to the left and down, which is toward the equilibrium position down here. So the pendulum will swing back and forth. It'll pass through the rest position each time. This motion has a period, a frequency, and an amplitude. The period is the time for one complete wave. In this case, it's the time for one complete pendulum cycle, one back and forth. The frequency is the number of cycles per second or per unit time, and the amplitude is the maximum displacement from the rest position, which could be measured from here to here or up to the other side. This maximum displacement can be pretty easily calculated using the length of the pendulum, the angle phi that it makes with the vertical. That may be a little tough to see, but it's up in here, and a little bit of trigonometry. So now the period of the pendulum, how long it takes to swing back and forth, is determined using the following formula. T for a pendulum is 2 pi square root of L over G. This formula is on your formula sheet. L is the length of the pendulum in meters, and G is the local acceleration due to gravity, typically 9.8 if you happen to be on the surface of the Earth. Now note in particular what's not in this formula. The mass of the bob doesn't matter, and its amplitude, or how high it's lifted above the equilibrium position, also doesn't matter. Only the length and local acceleration due to gravity. If you move the pendulum bob higher, it has a greater amplitude. It will swing faster through the rest position. Its velocity will be higher, but its frequency and its period will not change. Okay, the energy in this oscillation does depend on how high it is lifted. So it does, again, it's associated with the amplitude, and also how much work is required to lift the bob up to its initial height. So the formula mgh, h is the height above the rest position that the bob is lifted, G, of course, is the acceleration due to gravity, and M is the mass of the bob. This one's not on your formula sheet, so this one you want to remember. Now, as a simple harmonic oscillator, the pendulum would swing back and forth forever. In reality, of course, there are friction losses, particularly where the string meets the hook on top. This is where most of the friction losses take place. Energy is lost by the oscillation, so the bob doesn't swing quite as high on each successive cycle. As time goes on, the amplitude decreases. The period and the frequency don't change, and eventually the amplitude goes to 0, and then it stops moving completely. Now, the other type of oscillator we want to look at is called a spring mass system. We've seen this before when we did work and energy and looked at elasticity. We plotted spring force versus deformation to find the spring constant K. Recall that the spring constant can be described as how stiff the spring is. It's a measure of how hard it is to stretch the spring. The higher the K constant, the stiffer the spring. We hang the spring from a hook and then put a mass on the end of it. The spring will deform such that it reaches an equilibrium position where the spring force equals the weight of the mass. So mg would equal spring force Fs. Recall that spring force equals K times x, where x is the deformation or the change in the length of the spring. So at this equilibrium position, Kx equals mg. If we pull the mass below that point, so if this is the rest position, we pull it down here, the spring force increases, which makes the net force on the mass point upward, which is towards the rest position. If the mass is raised above the rest position up here, the spring force decreases, so the net force points downward because mg is greater. This combination of the spring force and the weight, the net force is the restoring force of a spring mass system. Whether it's above or below, the net force tends to want to bring the mass back to the rest position. So again, if we pull it down below, it wants to accelerate upward toward the rest position. It moves through that rest position with a velocity v up to some distance above the rest position. The net force now points down, so it then moves down and it goes back and forth. So again, this system has a period, a frequency, and an amplitude. The amplitude can simply be measured as the maximum displacement from the rest position, either above or below it. The period is determined using a formula very similar to the pendulum period. Again, it's on your formula sheet. 2 pi square root of m over k. M is the mass on the spring. K is the spring constant. Note, once again, that the amplitude is not in this formula. How far the mass is pulled above or below has nothing to do with its period or frequency. Again, if you pull it down further from the rest position, it will move faster. As it goes through the rest position, its velocity will be greater, but the frequency and period will not change. The energy in the oscillation does depend on the amplitude. Again, just like a wave, the amplitude and the energy are related. The energy in a spring mass system is 1/2 Ka squared. K is the spring constant. A, of course, is the amplitude or the maximum displacement. Just like a pendulum, if we treat this as a simple harmonic oscillator, the mass would bounce up and down forever. There is internal friction in the spring. Friction losses take place and energy decreases over time, so the mass doesn't move as far away from the rest position on each successive cycle. Just like a pendulum, the amplitude decreases as energy is lost, but the period and frequency do not. Now, if we idealize simple harmonic motion in which no energy is lost, if you plot the object's position as a function of time, the graph would look just like a transverse waveform. It would be a perfect sine curve. In reality, energy is lost, so the amplitude decreases with time with each successive cycle. This is called damped harmonic motion. Again, the period and the frequency remain the same, but the amplitude decreases. You might recognize these curves as exponential decay. One good application of damped harmonic motion is the shock absorbers in a car. At each corner of the vehicle, there's a large coil spring and a shock absorber inside it. The shock absorbers are inside the coil spring, as you see here. The shock absorber is a large cylindrical piston filled with liquid or gas. When the shocks go bad, and they don't damp the motion as well anymore, the car goes over a bump and it keeps bouncing up and down because the damping depends on the shock absorbers. And when they go bad, they don't damp anymore. And that's how you know. All right, that's it for simple harmonic motion. Next up, we'll look at some one-dimensional wave behaviors. And until then, enjoy. See you again soon.